Okay, let's get started. So hi there, I'm Stephan T. Lavavej, and I work on Microsoft Visual C++'s implementation of the STL. Yes, I know some people say, oh, don't call it the STL. As an STL maintainer, I declare I have the sovereign right to call the library what I think it should be called, and that's the STL. Today I'm going to talk to you about Tuple, which has been in there since CS+11. It goes all the way back to TR1, if you remember what that was. Today I'll be talking about what's new starting with 11, what was added in CS+14 and 17, and then implementation techniques. I believe I can guarantee that everyone here will learn at least one thing today, and that includes you, fellow standard library maintainers. A few things before we get started. Please hold your questions until the end. I have these fancy things called slide numbers. They're at the upper right. If you have a question or correction, just write down the slide number on your smartphone, and then we'll get to it at the end. Hopefully, we should have some time for questions. Also, everything I'm going to talk about is standard. I left an unless otherwise specified in there just in case. Turns out I'm not actually going to talk about any non-standard behavior, I believe. And if I do, I'll mention it. And by the way, everything I'm going to talk about is actually available for you to use right now in Visual Studio 2015 Update 3, the thing that's actually available right now, except for the stuff that was literally just voted into the standard, CS+17's apply, make from tuple, and get for const tuple ref, and I'll mention the implementation status of those at the end. So what is the most important issue I'm going to cover in my talk today? That is the pronunciation of tuple. Yeah. This is what the other standard library implementers need to learn too. You pronounce it tuple, not tuple. And there's a reason for this. It's super versus supper. There's no such word as supple, but there is the word supple. There is the word suplex versus an imaginary suplex, hence tuple versus tuple. Total ordinary rules for C++. So from now on, if you catch anybody saying tuple, yeah, point them to YouTube, marked at this point in time, and it's pronounced tuple. Tuple, okay. So that was the most important thing, if you learn nothing else. So now let's actually look at some technical stuff. Yeah, whatever. CS+11. So tuple actually does a whole lot. And yeah, you may have used it once or twice, but you may not be fully aware of everything that it could do in CS+11. So I tried to think of various examples that you would use a tuple for. And they range from fairly simple to fairly complicated. The simplest one that people think of is, oh, what if I want to return multiple values from a function? Well, even back in CS+98, CS+98 needed to be able to return an iterator and a bool from map insertion. So you get pair, iterator, bool. I think it's that order. I always have to look at the class definition to remember. But what if you want more than two? Well, that's where tuple comes in. So here I have a function starship. I can return a tuple of a string int string. I can say return make tuple. And then in main, I can store that in a local variable. I could use auto for this, or I could also declare tuple string int string. And then I can individually get elements from it, zero indexed, of course, because zero index is awesome. And then I can print out in whatever form I like. And by the way, all of my examples are fully worked and verified with online compilers in the various modes. The only thing I'm omitting are the includes and the using namespace stood, just because I'm trying to make the code actually visible. So this is sort of the hello world of using a tuple. But you can also make data structures out of tuples. This is actually something I do fairly frequently. You can make a vector of tuple. You can have a map where the key is a single element and the data type's a tuple, or vice versa. So here I have a vector of tuples of two strings and an int. I can list initialize it, which is pretty cool. I can iterate through it and again grab the 0, 1, 2 and elements and print them out. Now I could have had a struct with named data members, but I can just say, I don't want to bother naming them. I can just have a tuple. Now, moving into more advanced, that you may not have seen, although maybe you've heard of it before, you can also use tuple to make your own code simpler. So for example, say I've got a point here, a point struct, it could be a class, and I would like to implement lexicographic comparison. This is something that programmers are notoriously bad at. It's totally possible to write a correct lexicographic comparison, but many people get it wrong. And if you use tuple to implement it for you, well, tuple knows how to do it correctly. So all you need to do is you can say, I'm going to tie my data members x, y, and z, and then compare them using operator less than on tuples to tie of the other pairs x, y, and z. And this will correctly compare the first element, and if it can resolve the comparison there, it will return true or false. If they happen to be equivalent, then it will move on to the second element, and so forth. And it's a nice sort of one-liner way to do kind of what the core language should be doing for you, but doesn't anyways. So implementing comparisons is one thing you can do with tuple. Another much more advanced thing, but still C++11, is you can actually use tuple with pair. Now you might think, oh, certainly tuple is built on pair and not the other way around, but it is actually the other way around. If you have a tuple of A and B and you would like to construct A and B from individual lists of arguments, well, there's no such thing in C++ as having multiple function argument lists to constructors. But it turns out you can pack arguments in tuples and then give them to pairs constructor with a special tag called piecewise construct. And the helper function used to do this is called forward as tuple. And this allows you to do something that would otherwise be impossible. Because yeah, you can always assign to things later once they're in the pair, but to construct them for the first time, you only get one chance. And if you want to construct them with less or more than one argument, fewer or more than one argument, then you would use forward as tuple. So here I'm just showing vector because that was the simplest thing I could think of. I can either construct it in the pair from 0 arguments or a couple arguments to say 3 copies of 1729 and then print out their sizes. So that's piecewise construction. Now curiously, there's no such thing as piecewise construction for tuples. Perhaps there should be. Perhaps I'll write a proposal someday. For now, you only get it for pairs. And this actually turns out to be quite useful because things like maps, their actual value types are pairs. And map internally uses piecewise construction for things like emplacement and so forth. Finally, you can use tuple to store variadic data members. Now, this is in the example section. There's no actual example here. I'll explain that in a bit. So let's think about the examples that we've seen. I like to say the tuple is the world's laziest struct, and this is not really a compliment. Things like returning multiple values out of a function or even making data structures, you can always use like a struct with named data members. And if you use a tuple, you're basically saying, I am so lazy, I just can't bear to lift my fingers and type names of data members. It's just too much work. I just want to call them 0, 1, and 2. Super lazy. Now sometimes laziness is called for. Sometimes you only need it for a few lines of code. But you are being kind of lazy, and you really shouldn't allow tuples in this sense to sort of spread throughout your program, because now you're losing things like names on your data members or class invariants, because tuple is just a struct. It imposes no order, no higher level order on its data member state. Now, when it comes to things like implementing comparisons, there it gets much more convenient. I like to think of it as compensating for an outright deficiency in the core language, that it will not generate comparisons for you by default. That was proposed and rejected for CS+17. Maybe we'll get it in the future, but in the meantime, the standard library can help you out. Things like piecewise construction, that's literally your only choice. You have no other way to construct the members of a pair in place. Now, when it comes to variadic data members, I basically say that tuple is your only good choice, because there's no way in a variadic template to say, types ... members and get sort of a variadic pack of data members. It'd be really cool if you could do that, but you can't. And instead, if you ever are working with variadic templates in C++11 or beyond, and you would like to be able to store data members, tuple is kind of your only choice. It's that or re-implement it yourself, and you really do not want to implement anything that looks like a tuple ever. Ask any standard library implementer, they'll tell you no, use our stuff, we'll suffer so you don't have to. The reason why I do not have an actual fully worked example on this slide is that working with variadic data members inside a tuple in CS+11 was kind of obnoxious. Turns out you really want to have CS+14's integer sequence, and unfortunately CS+14 is the current standard, so I don't need to write anything as old and nasty as CS+11 anymore. If you're stuck on a CS+11 only compiler, I'm sorry. Get your employer to upgrade. Okay, so we'll see actually how to do this with integer sequence in a bit. Okay, so that's just a high-level overview of the things that you can do with tuple. Now let's look at all of the features in CS+11 so we can distinguish what existed in 11 and what is new in CS+14. Okay, so there are 4 different functions that return tuples in CS+11, non-member functions. And it can be kind of confusing. What's the difference between make from tuple and tie, and can CS+17's deduction for constructors replace these? The answer is actually no. People will tell you that, oh, you can just say tuple and the deduction will totally replace make from tuple, and that's actually incorrect. Make from tuple does a little bit extra work. Just like make pair, it actually follows the exact same convention. It decays what you give it. So if you say make tuple, and that's where this vtypes thing comes in, that's actually copied right from the standard. If you say make tuple and you mention the name of an array and the name of a function and const reference, make tuple will decay its arguments. So arrays decay to pointers, functions decay to function pointers, top level references and CV qualifiers are stripped. And this is desirable for various reasons. The other thing that make tuple does that not even CS+17's deduction for constructors does is it unref wraps. So if you have a thing that's called a reference wrapper, which is a standard library type, make tuple actually says, oh, I can give you an actual reference to the thing inside. Questionable whether anybody actually uses that functionality, but it's there, and make tuple does it, and so does make pair. By the way, and this is a common mistake I ranted years ago, don't help the compiler. It's still true, don't help the compiler. Never ever pass explicit template arguments to make tuple, because you are defeating the point. Either say tuple and then name the exact types that you want, or say make tuple and let template argument deduction do its thing. But in no case should you ever give explicit template arguments to make tuple. Another maker of tuples is tie that we saw before in the implementing comparisons. It can be used for other things as well. What it does is it takes a bunch of L-value references, it could be const, they could be modifiable, and it returns a tuple of L-value references. And it can be used for assignment. We'll see that on the next slide. A significantly more advanced version is this forward is tuple that we saw for piecewise construction. This requires a little bit of understanding, okay, a lot of understanding of R-value references and perfect forwarding. But it basically takes arbitrary stuff and returns L-value references or R-value references, a tuple of them. So if you call it with arbitrary things, you get a tuple that refers to them. The problem, though, the gotcha, is that because forward is tuple can take R values and return a tuple of R value references potentially. If you store that somewhere, what if those R values are actually temporaries that evaporate? Now you've got dangling references. So be very careful when you use forward as tuple that you're essentially immediately consuming it, that you're giving it to something like piecewise construct or tuplecat or something else. Don't store it for a long time. Even after a period of one function call, because what if those temporaries have evaporated? There's a note in the standard to that effect, but I'm going to repeat it anyways. And then there's tuplecat, which although its name is awesome, I've never actually seen it used for in production. It is super fun to implement, like unbelievably fun with integer sequences everywhere, but I just can't imagine an actual use for it. But it's standard, so there you go. That was CS+11. Okay, so I mentioned that tie can be used for assignment. Here's an example. So imagine I've got that exact same function Starship returning a tuple. What if I already have a few variables that I've already defined, string s into I, and what if I would like to assign to them? Well, I could always say I'm going to have a tuple, maybe defined with auto, and then say, okay, s equals get 0, I equals get 1 from the tuple. But if I would like to sort of take a shortcut, I could simply say tie s and I together and just assign Starship. And what this does is it constructs a tuple of string ref, int ref, and thing, and then that tuple, which is a temporary, is then assigned to the return value of Starship. And tuple has an assignment operator that has been defined to work specially for references. And it says, I'm going to assign through to the things that I refer to. So when I assign this tuple of string int string to my tuple of string ref, int ref, and stuff on the stack, this temporary, it's going to assign through to the string s and the int I. Then there's this thing called std_ignore that can participate in this, and assignments to it are ignored. I kind of view this as over-engineering. It's convenient to show, and I know everybody likes to see it for the first time when they work with tuples. I've never actually used it in my own code. It's not outright wrong, but I don't view it as a powerful motivator for tuple. I'm actually kind of scared of tuple of references. Now, it's certainly the case that piecewise construction and forward as tuple are super awesome, but when it comes to this assign through a reference thing that's actually powered by actual standard library code, it makes me nervous. When you have reference data members in a core language struct, there's a rule that says the compiler-generated copy assignment operator is inhibited. I will not generate such a thing for you. You can write it yourself, but the compiler is not going to help you. And the standard library looked at this in CS+11 and said for both pair and tuple, I want to be able to have not only pairs and tuples of references, I want to be able to sign through to them because I want to make std_tie work. Now, it's certainly the case that pair and tuple provide lots of functionality beyond the core language, like implicitly generated comparisons and conversions that you don't get with structs by default. And in general, these are super awesome. I love the fact that tuple of const_char star will implicitly convert to a tuple of std_string. That's wonderful. I'm not even of the opinion that that should happen for structs by default, but the fact that it happens for tuple is great. However, when it comes to this reference thing, it makes me nervous because it's kind of a hole in the type system. The example I have there in red at the bottom is that vectors and other STL containers require actual object types. Object type means not a reference, not a function, and not void. So that means that it is always and is currently forbidden to have a vector of int ref. That's just super weird and bad, don't do it. However, you can actually say vector of tuple of tref. The standard library won't actually stop you, and yet imagine what happens whenever the vector tries to assign its elements. Instead of assigning, in some sense, the tuples and repointing them as a reference wrapper would, that's a totally fine thing to put in a vector. But if you have a vector of tuple tref, any attempt to assign those elements will instead assign through to the t's that they refer to, and you're going to get totally jumbled up things. So don't ever write that, don't even think it, and this makes tie sort of scary for me when used for assignments like this. Now, tie for comparison is totally fine because you're not punching through the tuple and assigning to anything. Okay, the other things in CS+11 are ways to query tuples. You can ask, what is your size? Meaning how many elements are in this tuple, potentially 0 for a tuple bracket bracket. You can also ask, what is the type at index I? You could, of course, write these non-intrusively yourself, but they're just so common that the standard library provides them. The standard library, even though it took a little while to get correct in terms of what headers provide these things, but they eventually found the right answers. These type traits ignore top-level CV qualifiers just like all the primary type categories do. If you've ever worked with type traits, you will be familiar with the fact that you can say is integral on T, and if T happens to be const int, the answer is still yes. Like, yeah, const int is an int. However, references do change the answers given to the primary type categories, and similarly, if you give references to tuple size and tuple element, they won't work. They basically say, I don't know what this is. This comes up in perfect forwarding. Everyone, up to and including the committee itself in working drafts of the standard library standard E's, has made the mistake of writing a perfect forwarder, inspecting T with tuple size and tuple element, and forgetting that an L value reference can sneak in there. So if you ever work with these and you're working in generic code, keep in the back of your head, hey, maybe I need to deal with references. We'll see examples of this later. And these have been defined generically to also work with pairs and arrays. So here's an example of using them. I'm actually going a little bit out of order because I tried to write this with CS+11 and I could, but it was really annoying and made the font really tiny. So I've highlighted in purple here the things that I sort of borrowed from CS+14. I could write a function called getBack, and this is basically saying, what if I had a tuple of 3 elements and I want to get the third one, the one in index 2? The standard library won't help me with that, but I can write my own. So here I write a perfectly forwarding function that takes some arbitrary tuple ref, and I want to get the n-1th element. Well, how can I express the concept n-1? Well, I simply say, what is the tuple size of this thing, and then subtract 1. But when I say what is the tuple size of this thing, I can't simply say capital tuple, because if I'm called with an L value, that could be an L value reference type. So I need to remove reference from it. And in CS+11, this would be type name, remove reference of capital tuple double : type. That's horrible. So I use CS+14's remove reference T. And then I could also form the return type of this function using only C++11 technology. It would just need both tuple size and tuple element, and I would need to remove reference, and I would need to say type name. And at that point, I threw up my hands and I said, this slide was getting too dense. Let's just use decal type auto. And so this is how I would write a completely generic getBack function that respects value categories. We'll see a little bit more about that. But there's nothing preventing me from doing it in CS+11. It would just be a little bit more verbose. Okay. So I mentioned value categories. Here are all the overloads of get by index in CS+11. There are 3 of them. For tuples, there's also overloads for arrays and pairs, which I won't be listing here. So if I'm given an L value tuple, I get an L value reference. If I'm given an R value tuple, I get reference collapsing, because remember, tuple elements can also be L value or R value references in addition to plain old object types. This is actually sort of very dense. If you ever work with tuples in a generic context, I highly recommend just sitting down and working through what happens with the various get functions when called with L value or R value tuples, and when their data member types are objects versus L value references versus R value references, and what happens with the constants and L value qualifiers. Basically, what happens is that if your tuple is an L value, that propagates, and that affects the return type of get, saying that, oh, if you have an L value tuple and you get the first element of it, say the element is actually an int, get will return an int ref, because you can say that over and over, and when you can repeatedly name something, that's an L value. Whereas if you have a temporary tuple containing an int, and you ask what is its 0th member, and say that member is a string, then get will return string ref ref, saying, oh, you had a temporary tuple and you had an object living inside it. Well, when I get it, I know nobody else can be referring to this thing, so I'll give you an R value reference. And this also applies to reference collapsing, blah, blah, blah. So if you're writing generic template code that works with tuples, please remember that get interacts with value categories in a very well-designed way. This is wonderful. But you also need to remember it mostly so that you don't infect your tuples with L value-ness when you don't intend to. And the type here, E here, is just for shorthand. I've introduced it is tuple element, blah, blah, blah type. Okay. So if you've ever worked with boost tuple, there's a difference between boost tuple and stood tuple, and it's the fact that get is a non-member function. This is unlike dot first and dot second in a pair. And there is a reason for this. It's just not a very good reason. I can't defend it, but it's what the committee chose. The rationale is that if you were ever in templated code and you needed to say get, you would need to introduce template disambiguation, which I have seen repeatedly is something that comes up maybe every year on our internal CS+ mailing list at Microsoft, where somebody's writing code and it's rejected by a compiler, often Clang or something, and they're like, why do I need to disambiguate it? And then somebody has to explain it. And there's a whole reason. You can read CS+ Templates, The Complete Guide by Van der Voort and Jasudis. That's a wonderful book. It explains this in great detail. Basically, the compiler needs to know what things could be template names in order to understand what the left angle bracket could mean. By default, it doesn't expect template names. And in this case, it needs to be told, hey, get is a template. So t.template get is admittedly ugly and horrifying. And the committee said, if we make get a non-member, then nobody will ever need to say that. But the downside is that in non-templated code, you still need to write it as a non-member. That's kind of lame. I kind of like boost. Boost gives you both, and you can use whichever form is good. So if you care, write a proposal. Maybe I'll care enough to write a proposal. Maybe not. I'm a little bit lazy. OK. So that's everything, all the features that you could do to tuple in CS+11. Now let's move to CS+14, the current standard. This has introduced a few new things that can actually be very convenient for quality of life. Get by type. Integer sequence is technically not a tuple feature, but it's always used with tuples, so I'll cover that. Also, tuple received a lot of constexpr. I won't be covering that. If you like constexpr evaluation, tuple in CS+14 is there to help you. And a one-liner paper, basically, that added a template alias tuple element t in addition to things like remove reference t and so forth. So what's this get by type thing? This is actually extremely convenient. So it can be awkward in code when you see a lot of get 0, get 1, get 2, and you're like, what's the type of this thing? I need to go look at the tuple and then count 0 indexed what this thing is. Get by type basically says, oh, CS+, the core language is very convenient sometimes. It doesn't always get in our way. And one of the cool things it can do is you can overload templates based on type versus non-type arguments. So yeah, get takes indices 0, 1, and 2, but you can also overload it to take type parameters as explicit template arguments. And those overloads actually totally coexist. So here I've got an example where I've got a tuple of int stood string, const star stood string. And using get by type, I can say get the int data member out of it, get the const star. I don't know what position it is, but please get it. And this will totally compile in CS+14. Now there is a restriction, and the example sort of suggests it. What happens if there's a duplicate? Well, in that case, saying get string would be ambiguous. Like, which one do you want? The one at position 1 or the one at position 3? And wisely, the standard library says, oh, if there's duplicates, trying to use get by type for that specific type will be a compiler error. It's okay, and as the example shows, to get int when there are duplicate strings. That's totally fine. It's just you can't say get string. It's sort of enforced at the time you mention the type. So get by index is still the fundamental form, but in non-generic code, being able to say get a specific type is often quite convenient. So this has expanded the number of get overloads in CS+14, but they're very systematic. Again, they're overloaded for L values versus R values versus const L value tuples. So it's still propagating L valueness and constness. The fact that sometimes the information is provided through an index and sometimes the information is provided by a type does not affect that behavior of get. So yeah, it's more overloads, but it doesn't really add extra complexity. The complexity is internal to the library where we need to figure out, oh, you gave us the type int, what index is it, and is it unique? But that all happens internally. It doesn't expose anything on the interface, which is nice. And of course, there's overloads for pair. There is no get by type for array for obvious reasons. It only has get by index. But I didn't really have points, bullet points for that there. So integer sequence. Integer sequence, if you've ever looked at the standard, is a little confusing because the actual verbiage it devotes to it is not that much. A lot of it is actually hiding in the synopsis of the header utility. So at its heart, integer sequence is a struct. It's a tag type that exists kind of like integral constant, except for packs of integers. These could be int, it could be bool, it could also be size t, that's a very common one. The fundamental ones are integer sequence, and the usage there would just look like integer sequence int 1, 7, 2, 9. It doesn't care what you give. They could be duplicates, they could be non-ascending, they could be negative, there could be none of them, that's also totally fine. And then there's an alias template called make integer sequence. And here you could say make integer sequence int, 5, and this will become the type integer sequence int 0, 1, 2, 3, 4, counting from 0 up to n-1. And then there are some convenience aliases, index sequence, make index sequence, and index sequence 4 that are specifically for size t's. And these come up all the time, especially because tuple happens to be indexed with size t's. But they're not necessary. You could always just use the fundamental forms integer sequence and make integer sequence. So funny story. Make integer sequence can be implemented library only. You recurse at compile time with nested, recursive structs, inheritance, and manually form the type integer sequence in 0, 1, 2, 3, 4, and then stop counting at some point. So we had a user submit a bug report saying, hey, this is kind of slow, and if I ever ask for make integer sequence like 450, well, the compiler takes a really long time, and then it runs out of memory, and then it crashes. I would like it not to crash, and maybe be faster, but mostly not crash. And I looked at this and I said, yeah, okay, kind of, but 450 is huge. I don't have a lot of sympathy for this. Then they said, oh, but other implementers are clever. They have a logarithmic implementation that does something fancy and only makes log n specializations. And I heard, oh man, other implementers are doing better than I am. I got to do something about this bug. But then I said, I'm actually kind of lazy, and I don't want to have to figure out how to make a logarithmic implementation. I know what I can do. I can go to the compiler and say, hey, compiler devs, do my job for me. So I literally walk over to John Caves' office, or Jonathan Emmett, I think I harassed one of them, and I said, hey, could you do my job for me? And they're like, oh, okay. And then I also had to request this thing from the other front ends that we support, Clang and EDG. And so what we are actually shipping in Visual Studio right now, the definition to make integer sequence is right there, formatted for whitespace. We simply call a compiler hook and say, make integer seq, _. The type I want to form is integer sequence, and here's the type, and here's the size, and make it for me. Because the compiler can spam out the indices 0, 1, 2, 3, 4, 5, 6 up to 499 way, way faster than any conceivable standard library implementation using less memory. And this actually turns out to be a little important in somewhat pathological template code that really forms a lot of integer sequences. And it's also simpler for me to maintain, because if any bugs come in, I just file them under the front end path, and then I'm done. I wash my hands of it. Oh, make integer seq is broken. Well, that's the compiler's fault. So all the front ends implement this. I also mentioned this to GCC's maintainers and libstd CS+'s maintainers, even though as of right now, our STL doesn't need to target GCC. I said, hey, maybe they want to have the same sort of hook. So if you're using a sufficiently updated compiler, make integer sequence is way, way faster. And the way that I specified this, I was thinking, even though I only care about the STL, what if Boost wants to have a Boost integer sequence? Well, this thing is parameterized. So if somebody else has a third-party library with an integer sequence-like type, they can still have access to the same compiler hook as long as it behaves enough like integer sequence. So now that we have integer sequence and make integer sequence, what does it look like when we work with variadic data members? Now I can show you. So although I have ranted that bind is not very cool in the age of lambdas, it is a very convenient way to demonstrate variadic data members. And it actually does come up in situations like call once, stood thread, other things that take arbitrary numbers of arguments and then need to communicate them elsewhere and would really like to store them as data members. So here I have a struct which I have inventively called mini-binder, and it's going to store some callable object. In this case, I think, yeah, it's just going to be a plain old function object f called member underscore f, and then I'm going to have a tuple of args. Now, in the mini-binder constructor, which I've marked as explicit because maybe it could be unary and explicit is good, I am not going to try to deal with arbitrary value categories. I would do that if I had to maintain bind, and I do have to maintain bind, which is awful. But right now I'm not maintaining bind, so I got to be lazy, and I'm just going to take my value and decay, and I know it's going to copy, that's fine. I'm just going to store the stuff. Then in my function call operator, look at the bottom one for a moment. I'm going to just be a const function call operator. I'm not going to deal with constness and value categories. I'm just always going to be const. The first thing I'm going to do is I'm going to say, okay, I am a mini binder for the function object f and some number of args, maybe int string int. I would like to form an index sequence for the types int, string, int, or whatever. So if we look at the definition of index sequence 4, this says, okay, we need to get size of dot dot t. So if the types are like int, string, int, well, the size of dot dot, that pack, is 3. And so it says make index sequence 3. And then that expands to make integer sequence size t of 3. And then that becomes the type integer sequence of size t. And then the indices are 0, 1, and 2. And these are exactly the indices that I need to access a tuple of string and string or whatever the types that I said. 3 of them would be accessed with 0, 1, 2. So now that I have formed that type, I make an object of that tag type. That's those empty braces in the lower right. I could have used parentheses as well, but empty braces reinforces the fact that this is a tag object and not a function. So once I've got a tag object of type integer sequence size t 0, 1, 2, which the alias index sequence 0, 1, 2 means the same thing, now I can pass that to my helper, which I've called call. And then this can use size t dot dot idexes, and the compiler will now know that idexes means 0, 1, and 2, and I can use pack expansion to say, okay, I want to call member underscore f with get idexes of member underscore t dot dot, and this will expand for a 3 tuple into call mf with get 0 of mt, comma get 1 of mt, comma get 2 of mt, and then actually call the function. So usage looks like this. Imagine I've got a function add that takes 4 ints. I can call mini bind and say, okay, I'm going to bind to the function add to the integers 1,729. This will make a data member tuple int, 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 and then call will form the integer sequence size t 0, 1, 2, 3, and then actually call my add function. And so then I can call mb with no args, and it goes through the function call operator, my call helper, and it adds them all together, and I get 1729. Now, I could have written this in CS+11 either by writing something like make integer sequence by hand, or I could have written it recursively. But when working with variadic templates in general, and tuples specifically, please do not write variadic recursive implementations that peel off an argument and then add it to something and then peel off another. It's terrible for compile time, for correctness. It's very difficult to get right. When you work with pack expansions and integer sequences, it may seem strange at first. It requires a change in mindset. But once you switch over to that mindset, then you can write very efficient, very simple code that forms parameter packs like index sequence 0, 1, 2, and then applies them to a tuple in what I think of as a single variadic blast. And it's both efficient to compile and simpler to maintain. Essentially everything in the STL that works with tuples is now implemented with index sequence up to and including the monstrously complicated tuple can't. So that's variadic data members. Now let's move on to CS+17. So what does this look like? So in CppCon, we have apply, make from tuple. We've got logical operator type traits, which are strictly speaking not part of tuple, but they're very convenient in implementing the final feature, which is perhaps ominously called improving pair and tuple. I didn't make up that name. It really did improve them and made them complicated, but cool, so we'll see that. But first, apply and make from tuple. So apply and make from tuple are so simple that I can just depict the implementation that is literally in the standard library standard E's. So apply takes some arbitrary callable object f and an arbitrary tupleoid. It could be a tuple, it could be a pair, it could be an array. And it forms an index sequence, and then it calls invoke, which you may have heard of from my previous presentation last year about functional, and it gives it the callable object and the unpacked members of the tuple. So what does this look like? Here I've highlighted the relevant parts. So what apply takes and the eventual invocation, and everything else is essentially boilerplate, saying, yes, I need to take the type tuple, here they're using decay, get the tuple size, make the index sequence, then pass it to a helper, which now has size t ... but eventually it just unpacks everything. So usage is actually kind of simple. So imagine I have a tuple of arguments, and here, same sort of deal. I've got add that takes 4 ints. If I have a tuple of 4 ints, I can just say I want to apply this callable object, which happens to be the function add, to my 4 tuple of integers, and just invoke it. And there I add them all up. And because apply is generic, I can also apply the function object std plus to just a pair, because pair follows the tuple protocol. It supports things like tuple size, tuple element, and get, and apply will work with it directly. So I can also do this. This could be quite useful if you have a tuple of data members and you would like to just invoke some function object on them, but you don't want to write essentially this stuff. The standard library can do it for you. Now, in the core language, there's one kind of function that you can't actually get the address of, and that's a constructor. What if you want to construct a thing from a bunch of elements of a tuple? Well, that's where make from tuple comes in. Essentially the same thing. Make from tuple takes a tuple perfectly forwarded, so it respects value categories and all that, and it takes a type as an explicit template argument. And it forms an index sequence, and then constructs a t with parentheses, not braces, and then returns that out. So if you ever want to construct an object from a tuple, CppCon make from tuple can do that. Here I've got a very simple example. If I have a tuple of a couple ints, and I could say make from tuple vector int, and this will construct the vector int from 3 and 1729. And because make from tuple uses parentheses, not braces, which all of the standard library uses parentheses in this context, just like make shared and all that, I don't get 2 integers that are 3 and 1729. I get 3 copies of 1729. The standard library may handle braces at some point. The problem is you can't perfectly forward them. Like tuple sort of serves that. Anyway, I could rant about this for years. Make from tuple, parentheses, could be convenient. Okay, so now I mentioned conjunction. This is moving on to the how it works part of my talk. So these conjunction, disjunction, and negation, they originally proposed as and, or, and not, I think with underscore somewhere, but the committee got their hands on it and bike-shedded the names. Now you have conjunction and disjunction and negation. Okay, so they're not ambiguous, and they're never going to cause confusion with those bizarre quasi-keywords that ISO 646 has. So conjunction. This is a meta-type trait, which sounds super scary, and it is scary, but it's really convenient when you work with type traits for a living. You basically give it a bunch of type traits, and it gives you the logical and of them, but it also short circuits, which is cool. And it does this inheritance thing, which may or may not be cool. I haven't actually found a use for it myself, because all of my type traits derive from either true type or false type, and I don't inject extra information to them in this context, but it could be useful, and it's not really any extra cost to provide. And conjunction is defined to be true type if you say conjunction of literally 0 types. This happens to be useful. Disjunction is basically the same, but logical or. And negation can negate a single type trait, but at the type trait level without going down to the Boolean level of getting double colon value. And we'll see very shortly why this is useful. So what is this about short circuiting? So if you've ever metaprogrammed, you may have encountered the fact that metaprogramming doesn't really short circuit because everything needs to be evaluatable at compile time. So if you ever say something like, type trait 1 double colon value and type trait 2 double colon value, both of those type traits will be instantiated. And if one of them blows up, well, you've got a problem. Sometimes it's okay if you can ask the question of both of them, but sometimes it's improper to even ask a question. Conjunction offers a way around this, which is sometimes a lot simpler than writing handwritten code. So here I have a somewhat realistic example. Imagine I want to ask a couple questions. First, is the type A the same as B, and is the type A constructible from X? And imagine that the overall condition I want is, I want A to be not the same as B, never, ever, ever, and I want A to be constructible from X. Conjunction will answer this. But if I list them in this order, conjunction will do something extra special. And that's, it evaluates the stuff in blue here first and says, okay, is the type A the same as B? And if it is, then it gets negated to false, and we know that logical and a false in anything is false. It short circuits right there and says, okay, A was the same as B, so I am going to return false, and I am not even going to instantiate is constructible AX value. I can still just form the type is constructible AX. That's fine. I can always form that type, but I don't ask for its double colon value. This can be very useful in situations like when the type, B and X are the same or so forth. It's a way to avoid asking questions that you don't want to know the answers to. This comes up in Tuple, actually. It can avoid infinite recursion. It can also potentially improve compiler throughput, but that's sort of a minor benefit. Disjunction also short circuits as a logical OR would, and that's also useful in various situations. So how were pair and tuple improved? In CS+11 and CS+14, there was a perfect forwarding constructor. Tuple of int-string int is constructible from three things, and they will be used in order to construct each data member, perfectly forwarded. Now this constructor was marked as being unconditionally explicit, which I've highlighted in red there. Why? Well, because what if you have a one tuple? Well, a one tuple would take one argument, and we all know we don't like implicitly converting constructors, especially when they take only one argument, because that could be used for implicit conversions. So Tuple's designer said, oh, we need to lock this down, we need to make it explicit. Totally the right call. In CS+17, this has been lifted. So now the standard library specifies these things with explicit in all capitals, monospace, and italic. And this is because it's trying to do something that the core language doesn't support yet, which is conditionally explicit constructors. There's conditional no except. You can say no except and then a bool, and then that's either yes, no except, or not. There's no way to say explicit paren and then some Boolean condition. I wish there were, because it would make my life somewhat easier. There's not. But we can make it anyways, even though we're not compiler devs. We can make it with library-only technology and what I refer to as on-off SFINAE. Okay, so why would you even want this? Here's an example. This example is specific to CS+17, and if you go all the way back, you need to use like GCC in CS+11 or 14 mode. This will be rejected. And if you use a sufficiently new GCC in CS+17 mode, this will be accepted. If you try to use libc++ with Clang, this appears to be accepted in all of their modes. I think because they've got a non-standard extension. Yes, Eric's sitting there. He maintains the thing. He knows. But technically, this was not valid CS+11-14. It is valid CS+17, and it will be accepted by the latest versions of all the standard libraries in CS+17 mode. What is it trying to do? Well, here I've got a print function that takes a const tuple string ref, and then it prints out elements. So if I want to be able to return a tuple string, previously I would have needed to say something like return make tuple of red, green, blue, or return tuple string, paren, red, green, blue, or similar horrible abominations. Now I can use braces. This uses CS+11 uniform initialization, but this actually requests an implicit conversion from 3 arguments to tuple string. And this is actually a CS+11 thing. Explicit is now relevant on constructors that are other than unary. We never used to think like this in CS+9803. Now it matters. And tuple has been revised in light of this fact. It's taken sort of everybody a little while to get used to. So now I can both brace return tuples, and I can pass braces to something expecting a tuple of a particular type, and that will implicitly invoke the perfect forwarding constructor and construct a tuple for me. And whereas previously the hard-coded explicit in CS+11 and 14 would have prevented that. Now this is conditionally explicit. It is implicit only when each individual element is implicitly convertible. In this case, I'm going from a decayed const char star to the type std string, and that is implicitly convertible. That's totally fine. However, if the types involved are not implicitly convertible, then the standard library detects this and says, okay, you can construct this thing or you can convert this thing, but you must do so explicitly. I will not do it implicitly for safety. So my usual example is vector. Vector of anything is constructible from an integer explicitly. I could say vector of string paren 5, and that will construct a vector of 5 default constructed strings. But I cannot say vector of string v equals 5. Copy initialization is considered implicit, and I am not allowed to implicitly go from an integer to a vector of anything. That's just too weird. So here, if I have a tuple of string and vector int, I can directly initialize it from a string and then the integer 3, and then this will directly initialize the vector int inside from 3. And I can print it out, and I get 3 elements all equal to 0. But if I try to print using list initialization, using these braces like I did in the previous example, this would try to construct a temporary string of temporary tuple of string and vector int. And that constructor, the perfect forwarding constructor, is explicit. It senses the fact that going from for to vector int requires this explicit conversion. So that would be a compiler error. The compiler error is admittedly horrible if you do not know what's going on here, but it's stopping you from writing bad code. Perhaps in the far future, compilers will actually be taught to provide higher level context rather than, or possibly even pop up a YouTube link to somebody explaining what's going on. We don't live in that magical world yet. Okay, so let's look at all of tuples constructors before we see how to actually implement this. First off, we start with the simple ones. These are tuples constructors in CS+17. You've got a default constructor, which is constexpr. You've got defaulted copy and move constructors. I'm ignoring the allocator argt spam. You don't want to know what it is. These are the simple ones. Then there are more constructors, and there are so many that I've needed to extract the templateness and put it on different bullet points. But here you can see actually how they're highly systematic. You've got one constructor, tuple const types ref, that is almost always outcompeted by the perfect forwarding constructor, tuple from arbitrary urefref. That first one exists so that people who are being horrible and saying something like tuple of double star comma stuff can construct that from the literal 0. And even though the type int cannot convert to double star, the literal 0 can, and this first constructor will be used in that case. I would prefer for it not to exist, but it exists for backcompat. Then you've got the converting copy constructor and converting move constructor for tuples. And this is quite useful. This is what allows you to convert a tuple of const char star to a tuple of std string. And finally, you have a couple of pair converting copy and move constructors that exist only for 2 tuples and allow you to convert between from pairs to tuples, which are convenient, but require dedicated constructors. So how do we implement this capital explicit thing? Let's see first, how do we even do SFINAE? So as far as I can think of, there's 5 different positions where SFINAE can appear in a function. Maybe there's more. Come up to me later and tell me. But here I've tried to list them all. So first, let's start off with a simple example. This is totally unrealistic. Add 0 that takes a t and an I, adds them together, and returns it using decal type to get the type correct and so forth. What if I wanted to constrain this thing to exist only for integral types t? The first and oldest thing that I could do is annotate the return type. I can wrap it in enable if t on the condition is integral v. This uses CS+17's variable templates for type traits. I could also say is integral t double colon value, same deal. If I wrap the return type, then when the compiler tries to substitute it, maybe the return type will vanish and the whole thing's SFINAEs, classic. The other thing I can do, which you probably have seen if you've written enable if in code, is I could add a default function argument. When I've done this, I like to use the type void double star, because that is actually pretty hard to get anything to convert to. There's other types you could use, but I usually just use void double star, and I can just default it to null putter. Another more obscure thing you can do is if you have a function argument that is not a template, you can wrap that type in enable if. Now, all of these are deficient in some way. The return type one is not applicable to constructors and conversion operators because they don't have classic return types. I don't think you can do it to conversion operators. In any event, too weird. The bit about the default function argument does not apply to variadic functions, including variadic constructors, because as soon as you try to put a default argument, now your parameter pack is non-deduced. And if you don't know what that means, it's horrible. And finally, the bit about, oh, what if you have a non-templated function argument? Sometimes you just don't have any of those. For example, tuples perfect forwarding constructor satisfies all of these criteria. There's no place to put any of these constraints. So the fourth and fifth ways to SFINAE are in default template arguments. The first way, which I've used most commonly, is to say, okay, I'm going to have type name, and it's going to be a dummy, so I'm not even going to bother naming it. I'm going to say enable if t is integral v, and I'm done. Another way is you can use a non-type template argument. You can say enable if t, and if the condition is good, form the type int, and then I want to have this non-type template argument int default to some value 0. It could be 1729, the value doesn't matter. I mean, I could use another type than int, I could use long or whatever, but I like int and 0 because they're less typing and I'm lazy. So why would one prefer one or the other? Turns out there is a difference, and the first one cannot be used for on-off SFINAE, and the second one can. So what does that look like? Here I've written what I am just calling, for the purposes of the slide, SFINAE dispatch. I could do this with tag dispatch as well in this case, but for constructors I'm going to need this. So here I would like to turn on one overload for isIntegral, and then I would like to turn that off when the type is non-integral and use another overload. So here I've highlighted the difference. One is enabled for isIntegral, and the other one is enabled for not isIntegral. And I've used the int equals 0 form. The reason why this works is because when the compiler is trying to look at these things, and it sees, oh, I don't know what t is, so I don't know if these are exactly the same, so I'll let them coexist. And by the time I actually get around to template argument deduction and substitution, then I'll figure out what their actual template parameters look like, and then I'll see, okay, only one of them exists. If I tried to use the type name equals stuff form, and I had two identical signatures, what the compiler would see is, oh, you have two overloads that take the same function parameters, and they take the same kinds of template parameters, and they have different defaults. But the fact that they take the same kinds of template parameters means that, oh, you've got like duplicate overloads. I can't handle this, and it explodes. So if you use the int equals 0 form, you can turn on and off overloads with SFINAE. This is useful for constructors, where sometimes you don't want to use tag dispatch, and you just want to be able to control them right there. This is necessary for conditional explicit. So here I've got a type called wrap. Wrap is going to wrap a single type t. It's like a one tuple. And it is going to want to have perfect forwarding constructors from you that are conditionally explicit. This is actually very close to what tuple does, except only for one argument, to avoid exploding your heads horribly. So I've got an additional constraint here, not self. And this asks, okay, is the type u, after I remove referenceness and after I remove constness, is this the same as wrap? I want it to be not the same because I do not want to compete with my actual copy move constructor. Then, if I want to enable the implicitly converted constructor, I want three criteria to be true. And I'm going to say enable if t, conjunction v, meaning all of these things need to be true, logical and. First, I want u to be not myself, so I don't want to compete with the copy move CDORs. Second, I want t to be constructible from u, because I am actually going to construct the thing. This needs to be well formed. And finally, I would like u to be implicitly convertible to t. The order is convertible from to, that's why it appears reversed. That is intended. And if all those things are true, then I am not myself, I am constructible from this thing, and I am implicitly convertible. So it's okay for this constructor to be implicit. The other condition, which is purple here, is the condition to enable the explicit constructor. Again, I require u to be not myself, and I still need t to be constructible from u, because I am going to construct the thing with direct initialization. But I want to turn this thing on when u is not implicitly convertible to t. This is what senses the difference between const_char star implicitly converting to std string versus int not implicitly converting to std vector of t. And so if I define these alias templates, then I can define my wrap constructors. They both take arbitrary urefref. One is plain, one is explicit, and they're constrained by enable implicit versus enable explicit. And this allows it to behave just like tuple does. If I have wrap of string, I can implicitly or explicitly construct it from const_char stars after decay. In this case, it will actually take a reference to array of 5-character const characters, blah, blah, blah. If I wrap a vector of int, I can directly construct the thing from int, but I cannot implicitly construct. So this is how we implement conditional explicit. So I have a few minutes left. I'll quickly mention various tuple issues that have appeared in CS+17. Get has received overloads for const tuple ref. Turns out const R values are an important value category. You cannot forget them. It is a safety issue, although obscure. It fixes a subtle hole in the type system. But if you don't write highly generic code, you never need to know about this. Pair and tuples default constructors have been constrained. Turns out, yes, you can constrain a default constructor. You just template it and hope nobody notices. The theme here is that in generic code, you really need to constrain the existence of your constructors. And because pair and tuple are so fundamental, they need this level of attention. The various constructors, the perfect forwarding, the converting constructors have received arity constraints so that they don't exist for wrong argument numbers. There's a lot of controversy in the committee about this. Eventually, we realized that libcs+'s extension was evil because libcs+'s maintainers admitted it was evil, and they finally realized it. And so now we have these arity constraints so that this code is now well formed. Basically, 2 tuples are only constructible from 2 arguments, 2 tuples are only implicitly convertible to other 2 tuples, and so forth. It's essentially what you would expect. So you can now write code that depends on this, and it will work portably across the various implementations. Visual C++ has supported this for many years. There's been a very complicated code about ambiguity between perfect forwarding and converting. This has been resolved by preferring perfect forwarding constructors instead of the converting tuple constructors. This impacts your code if you are writing 1 tuples of types that are omni-constructible. So we could go into the issue. It's complicated. I got to load it up and remember exactly what's going on. It is a safety issue. This was not done lightly. And if you want to ever avoid thinking about this, when you have a type with a templated constructor, please constrain its existence to exist only when it will actually compile using enable if anybody will ever make a tuple. People have been complaining, oh, if I have a std tuple of a boost signals type, and the type is not properly constrained, then converting the tuple doesn't work, and it's because of this issue. It's pretty horrible. Constrain your constructors, and it won't be horrible. And finally, there's something that hasn't even been filed as an issue yet, but it turns out the perfect forwarding constructor can actually outcompete the copy move constructor, which is totally not desired by anybody. And although we have not actually filed an issue yet, all of the standard library implementers agree that the copy move constructor should win in this case. And we have updated our implementations to do that, even though the standard doesn't yet say so. This is actually exactly what the wrap type did in my example with that not self thing. That is taken directly from our production code. This avoids particularly egregious blowups. You never need to know about it because it has been fixed. So if you want to know more, I did mention everything here is available in VS 2015 Update 3. The only things that are missing are things that are voted into the standard very recently. Get for const tuple ref, all of those overloads have been implemented. They will appear in the next version, which is confusingly called VS 15 in air quotes. I did not name it. Apply and make from tuple, I implemented them locally on my machine. I was all ready to check them in on Monday, so I would not need this bullet point. And it passed my tests. And I ran it against libcs+'s tests with our compiler and our STL, and I immediately found 2 compiler bugs. Thank you, libc++. So I felt really bad about checking that in with those failures, so I'm not going to do that yet. I'm going to get back from CppCon, properly reduce the compiler bugs, then disable those tests and check the thing in. But I do expect it will get into VS 15. I just can't promise that yet. Everything here I've talked about is as of the current CS+17 working paper. There's the current link. This will change, but as of right now, that's what I'm referring to. So if you have further questions, you can email me. My address is there. It's very easy to remember. I'm also finally on Twitter, so you can follow me there. And I guess I have time to take 2 minutes worth of questions from the audience. So. Anybody have questions? Yeah, back there.
Did you get to compare the use of conjunction and disjunction against fold expressions?
The question is, have we compared conjunction and disjunction against fold expressions? And my answer is very simple. We don't have them in C1XX yet, so they don't exist for me yet. I imagine we will look at the difference between throughput and so forth. But right now, we haven't looked at fold expressions versus conjunction and disjunction. Yeah, question there. Slide 45. Slide 45. Oh, what's the compiler error if you get this sort of thing wrong? The problem with SFINAE is if it goes wrong, stuff just vanishes. Various compilers differ. Clang and GCC now will tell you, oh, I tried to call this thing, but I didn't actually find any overloads. I had to remove A and B because of criterion C and D. C1XX just says I couldn't find the thing. That will improve hopefully in the future. But yes, essentially the quality of error messages vary, and it's a hard problem because the tools that we have for constraining constructors like this are just to make them appear or disappear. It's a very blunt instrument. And I do feel bad for compilers when they have to emit diagnostics. Yeah, question there.
So slide 36.
Slide 36.
Do these implicit constructors, construction behavior extend to operator overloads?
Do these implicit construction behavior extend to operator overloads? Operator overloads are just functions. So tuple is only concerned about, am I constructing either from perfect forwarding or by converting from another tuple? It has no idea what context it is. Here, tuple only sees a call to its perfect forwarding constructor. It has no idea that I'm in a return or in a function call. So essentially, whatever context in the core language you're trying to invoke the stuff in, if it's considered implicit versus explicit according to the core language rules, that's what will determine what tuple does with it. So it looks like we're out of time. I'll be available later to answer your questions. Thanks for coming.